Hey Algebra 1, and thanks for tuning in. Today we're going to be looking at your Chapter 6 test review, so you should have your review right in front of you ready to go over the correct answers. So we're going to get started. The first section says simplify the expression, write your answer using positive exponents. So remember what we can do here is just maybe write a fraction and then determine where the new things will go. I know that 2 to the negative third power needs to go on the bottom to make it a positive exponent. X to the 0 is just going to cancel out and give you 1, so you really don't have to write that. And then y to the negative fourth power, that is going to need to go up at the top. So you can say y to the fourth over 2 to the third, but really 2 to the third can be simplified even more. So you're still going to keep y to the fourth on top, but 2 to the third is equal to 8. For number 2, that just means when we have at that negative exponent, everything is going to get a negative 4 to it. So again, what I like to do is to start by drawing my fraction and start distributing. 1 to the negative fourth power would be going on the bottom. So if you wanted to write that, you could, but you really don't have to. 3 to the negative fourth power would be going on the top. And then a to the third to the negative fourth power, that'd make it a to the 12th power. Because we're doing that power of power properties, 3 times 4 would give me 12. Now I'm ready to simplify. Again, 1 to the fourth is just 1, so basically we have the top numbers 3 to the fourth and 8 to the 12th. And then I can make 3 to the fourth be 81, and then a to the 12th would stay the same. For number 3, again, we're distributing everything, or we're giving everything inside the parentheses this 3. So I'm going to have negative 4 to the third power and x to the 6th power. Negative 4 to the third power is going to give me negative 64, and then keep x to the 6. The next few, we're going to evaluate the expression, the cube root of the cube root of 216, and then we're going to keep it negative. I know the cube root of 216 is 6, and then I'm just going to bring down the negative. So my answer to number 4 is negative 6. For number 5, this is written in exponential notation. It might help to write it in radical notation, so that's what I'm going to do. I'm going to bring this 3 around to the front, so put it in front of the radical, and then 64, and then to the 5th power. I know that the cube root of 64 is 4, and then I'm basically just going to be doing 4 to the 5th power, which is going to give me 1024. Again, for number 6, I'm going to rewrite this in radical notation, so I'm going to bring that 3 around to the front, so the cube root of negative 8, and then to the 2nd power. I should have done this before, putting them all in parentheses like that. The cube root of negative 8 is negative 2, and then I'm basically doing negative 2 to the 2nd power, which is a positive 4. For number 7 and 8, we're just going to determine if they are linear or exponential. Notice how number 7, your x's are increasing by 1, which is still fine, but then your y's are decreasing by 3. So this one would be linear because y is subtracting 3. For number 8, again, we see x is increasing by 1, but y is increasing by 2. So we're going to say that number 8 is exponential because your common difference, or excuse me, your common ratio is 2. Or you could say y is being multiplied by 2. For number 9, we're going to graph y is equal to the 1/3 x and describe the domain and range. So the first thing that would help you here is to maybe draw a table that we did, similar to the ones that we had in those guided notes. So I'm going to put my x and my y on the ends, and then I'm going to put my how to actually work it out here in the middle. And I notice that I have my ranges going up by 2s on the graph, so that might help me depending on where I'm putting that. I'm going to just use the values negative 2 to positive 2. Well, I'm going to go ahead and plug those in so we can see what those look like. So here I have created my x and y table. If I have an input of negative 2, my output is going to be a positive 9, and so on. So now I'm going to go ahead and graph. Again, make sure when you use negative numbers, you use the reciprocal of your fraction to get rid of your negative exponent. Let's see what the graph looks like. So here are my points plotted on the graph, and notice that, again, we always approach the horizontal asymptote, but it's never going to touch it. It does say to describe the domain and the range. Again, the domain will be all real numbers, because that's going to stretch from anywhere on the x-axis, essentially. As you go negative, it's going to grow, and as you go positive, it's also going to grow. The range just needs to be y would be greater than 0. So that's all we had to do there. I think the trickiest part maybe would be choosing your x inputs, but once you choose those, you should be fine. Next up, we have number 10. It says evaluate the expression for the given value of x. So that just means you're plugging in whatever x is equal to. So f of x would be equal to 3 times 4 to the x power. If we plug in -1, so f of -1, that'd be 3 times 4 to the negative first power. Again, anytime you have a negative exponent, you can write it as a reciprocal of that number. So we're technically doing 3 times 1/4. So f of -1 will give me 3/4. Over here, we just have y is equal to 0.5x, where x is to the -4th power. What I did here to maybe help myself is you could, in fact, change 0.5 to 1/2. If you left it as 0.5, that's fine. You'll still get the same answer as me, but this is what I did. So instead, I wrote this as y is equal to 1/2 to the x power. And then I plugged in the -4, and which means everything's going to get a 4th power, and it's going to flip. So if I maybe started here, 1 to the -4th over 2 to the -4th, that's just going to flip and give me 2 to the 4th over 1 to the 4th. The 1 to the 4th will just give me 1, and 2 to the 4th will give me 16. So my answer for number 11 is 16. Again, you should still get the same answer if you used the decimal form of 1/2. On the back side, we have the next few questions. Determine whether the function represents exponential growth or decay, and identify the percent rate of change. For this one, in number 12, this is a decay, and the percent of change is 3%. For number 13, this one would be a growth, and the rate of change is 30%. For number 14, I know it's a growth, so I'm going to go ahead and write growth. What I then have to do is just kind of piece together some information. So I know I want it to look like an exponential notation, which is in the form of y is equal to abx. So what I did first is said y is equal to 5, because 5 is going to be my initial amount. And then, since I did not know the percent change, I could still maybe determine what my final amount would be, or in what my original amount would be. So then I just took the last number in 625 and looked to see how it was growing. It was growing by timesing by 5 every single time. So that's my common ratio. So I can still say y is equal to 5 times 5 to the x power. So 5 is my original number, and then 5 would be my common ratio. I'm going to write CR. In order to make it look like the growth or decay formula, this piece right here has to be 1 plus or minus something. I know that I am adding because it's growing, so 1 plus what will give me 5? Well, I know 1 plus 4 will give me 5, so that's going to be what needs to be in my parentheses, which now I can tell what my percentage is. This number right here, the 4, is going to represent my percentage of growth. It is not in percent form. It's not 4% growth. Instead, it would be 400% growth. So therefore, it is a growth problem with 400% growth, because that 1 plus 4 needed to be able to make the common ratio of 5. For number 15, it says the function p of t is equal to 2,000 times 1.5 to the t power. And it represents the population of a small town. How many people are living in the town after 3 years? So after 3 years, that means t is equal to 3. So I'm just going to plug that into my formula. So P of t is equal to 2,000 times 1.5 to the third power. I know 1.5 to the third power, after doing some calculations, is 3.375. So I'm multiplying that by 2,000. So I'm going to get the town's population after 3 years is 6,750 people. Number 16, this is where you're going to use your formula of compounded interest. You do get the formula given to you, and this is what that formula looks like. Now we're ready to plug in the values. P is your principal or your starting amount, so I'm going to plug in 500. The next thing I can plug in is my percent. So 1 plus 0.07 will go on the top. And then I need to figure out what n is equal to. It does say it's compounded semi-annually, and n is the number of times it's compounded. So because it's compounded twice, I'm going to divide 0.07 by 2. And then I still have to multiply n, which is 2, times t, which is 4. So now I'm ready to go ahead and start my problem. I have 500 still, and then I'm going to go ahead and simplify what's in here. 1 plus the 0.07 divided in half is going to be 0.035, and then 2 times 4 is 8. So now all I have to do is add 1 plus 0.035 and then keep it to the 8th power. It doesn't say to solve, it just says to write the problem as you function and as you are trying to find the balance after 4 years. So y is equal to 500 parentheses 1.035 to the 8th power. For number 17, we're just solving. So just remember too, we want to have the exponents be the same thing, or sorry, we want bases to be the same and exponents to be the same. One way we can do that is make them both have a base of 3. So if we want to have a base of 3, we need to go ahead and change them to make a base of 3. I know 81 can simply be made into 3 to the 4th power, but this one over here might take a little bit of thinking. How did 3 get to the bottom? Because the exponent was negative. So this one would need to be 3 to the negative x power, to the negative 1x power. Now I'm ready to write them as equivalent equations. So negative x is equal to 4, which means x is equal to negative 4 after dividing both sides by negative 1. For number 18, again, we want the same base. Again, we start off with a 7 over here, and I know 7 can be made into 343. It probably will just need to be made into a negative exponent again. So 1 over 343 is the same thing as 7 to the negative 3rd power. So now I have 7 to the 5 minus 4x power and 7 to the negative 3rd power, which means now I can write them as equivalent equations. I'm going to go ahead and subtract 5 from both sides and get negative 4x is equal to negative 8. And once I divide by negative 4 on both sides, x is equal to a positive 2. For number 19, we're almost having same bases. Both of these numbers do have 5 in common. So what I would do is change 25 to be 5 squared times 2x to minus 3. And then 125 I'm going to change to 5 to the 3rd times x plus 1. Now I'm going to go ahead and just distribute this 2 on the first one. So I'll have 5 to the 4x minus 6, and the 3 I'm going to distribute on the second one. I'll have 5 to the 3x plus 3. Now I can go ahead and set 4x minus 6 is equal to 3x plus 3 equal to one another because they have the same base, and we'll be ready to go ahead and solve for x. I'm going to move my x's to the left side, constants to the right side. I get x is equal to 9. For number 20, we're just going to determine if the sequence is arithmetic, geometric, or neither. For this one's going to be arithmetic because the common difference is negative 1/2. For this one, we're going to say neither or neither because there's no common difference or common ratio. Okay. For 22, write the next three terms of the geometric sequence. It looks like we're multiplying by -2 each time. So what we're going to do is just keep multiplying by -2. So 40 times -2, that's 80. And then 80 times -2 would give me -160. And -160 times 2, that's going to give me a positive 320. So here are my next three items in my sequence for 22. For number 23, I am also multiplying by 2, which in turn is making it smaller every time. So my next three would be 1/4, and then 1/2, and then 1. Or maybe you could think about it as dividing the bottom number by 2, but you're still technically just cutting those in half. 24, write an equation for the nth term of the geometric sequence and then find a of 6. So what I need to do first is write my geometric sequence formula. So I'm going to have a of n first, and then a1 is my first term, so that's 3 over 125. And then r stands for my common ratio. Every time I'm multiplying this by 5, so my common ratio is 5. And then n minus 1. Now I'm ready to find a to 6. So I have 3 over 125 times 5, and then to the 6 minus 1. That is going to be a6 is equal to 3 over 125 times 5 to the 5th, which would give me, and I made 3 over 125 a decimal, 0.024 times 3,125, which is 75. So a of 6 is 75. And then for this one, my first term is 0.2, and then everything is being multiplied by 8. So 8 is my common ratio. Now I'm ready to find a of 6. So 0.2 times 8, parentheses 6 minus 1, that's going to be 0.2 times 8 to the 5th power, or 0.2 times a really big number, 32,768, and I will get 6,553.6. Okay, that's going to conclude our review for Chapter 6. Thanks so much for tuning in, and good luck on your test.